All right, folks. So let's have a look on some complex numbers. And this lecture is for Engineering Mathematics 1, and a short introduction on what complex numbers are and how can we use them. So the imaginary unit of I is essentially a definition of square root of -1. And the complex number is then just a pair of real numbers. Or could be considered a pair of real numbers, so coordinate points x and y. Here's z, where x is the real part. So if we project it to the real axis, and y is the imaginary part if we project the number to the imaginary axis. So the imaginary number in these coordinates is 0, 1, no real part, and 1 imaginary unit. This is originally calling names, so many contemporary mathematicians did not understand that why these would be useful and worth study. So first the imaginary unit was called, well, imaginary, and then also the operations that were necessary to calculate with these numbers were called complex operations. But there are applications on heat transfer, fluid dynamics, especially electronics, and so on. We are not going to go through phase spaces and things like that, just briefly what the arithmetics are. Equality, so just like vector math, so you have your x and y's, and if both components are equal, then two complex numbers are equal. Addition, as with vectors, so add up both components. Subtraction, as with vectors. Multiplication, we do have multiplication formula, so if we consider z1 and z2, two complex numbers, usually we call them z's, or use the z here. So, and their components are x1 and y1, x2 and y2. So then we have this formula, x1 times x2 minus y1 times y2. That's the real part. So if we call that as z equals z1 times z2, then this part is real value of z, and then this part x1 times y2, so the real part of first one times the imaginary part of second one, plus x2 times y1, the real part of the second number times the imaginary part of the first number. Then this would be the imaginary part of our product. And we can see that this is commutative, so z1 times z2 is z2 times z1. We can verify that these two work exactly right for if we have only a real number, and we also fulfill the condition that I squared must be -1, so that the square root of -1 ends up being I. We commonly write this in form as z equals x plus iy, or if we're working with electrical engineering, because I might mean the current, then we typically use J over here. For example, MATLAB understands that both variable named I or variable named J, if they have not been redefined, mean the imaginary unit. So then we go to subtraction. That's really easy. Just do that unit-wise or component-wise. But then the quotient gets slightly more complex. So we still need to have preserved that if we have a quotient z equals z1 by z2, where z2 cannot be a zero vector, then z1 must be z times z2. So we could work backwards there, but here's the formula. So the real part will be real parts multiplied plus imaginary parts multiplied divided by the square component-wise square of the well, nominator kind of here, so dividing value. And the complex part here to fulfill the previous is so this is the divisor first form writing. You occasionally see it in different forms, so x2 times y2 minus x1 times y2. Did I say it the wrong way? x2 y1 minus x1 y2. Well, you can read that. And the divisor is of course the same. And we will also introduce you another reasoning for this formulas, which will be easier to remember as well. So let's have an example. We have two complex numbers, z1 and z2. So here's z1, here's z2, and let's find the sum z1 minus z2, the product, and the quotient. So addition and subtraction are really easy. The sum is just sum by parts. So here are the real parts, here are the imaginary parts. Real parts sum up to 17, imaginary parts sum up to 1, which we usually do not write, so this plus I is the same as plus 1I. And then on subtraction, 8 minus 9 is minus 1, and 3 minus 2 is 5, and we get that. Multiplication. Okay, now we need to use the formula, so we present these numbers into a real imaginary pair form. So 8, 3, and 9 minus 2, and this minus there is meaningful, don't forget it. And apply the formula. 8 times 9, that's the real parts, minus 3 times minus 2, that's the imaginary parts multiplied, and that becomes the new real part. 8 times 9 is 72, and minus 3 times 2 is plus 6, so that's 78. And then we get the real part of the first one multiplied by the imaginary part of the second one, going to minus 16, and vice versa. Real part of the second one multiplied by the imaginary part of the first one, plus 27. Minus 16 plus 27 is 11. So what we get is 78 plus 11i. Division. Same numbers again. What's the quotient? So we have these formulas. The nominator of the quotient will be the same in both. That comes solely from the divisor, which of course is makes sense because, well, that's kind of what division is. And then x1 x2 plus y1 y2, like that. 72 minus 6 is 66, and imaginary part x2 y1 minus x1 y2 is 43, so we get that. You could essentially work your way from the multiplication formula, get these, but we'll for now skip the proof of that. If you're interested, that's rather easy to find. Okay, then the complex plane. So now let's consider that we're having a coordinate system. Almost can draw straight lines, so this is now the real axis and this is now the imaginary axis. For example, 1i is the point over there. Point 1 is that point over there. And our first number, 8 plus 3i, would be 1, 2, 3, 4, 5, 6, 7, 8, somewhere here, plus 3i, so somewhere there. That would be 8 plus 3i. And now we can see that addition and subtraction, that's just vector math. We do have this different kind of a multiplication operation. But before we go to that, let's introduce the concept of complex conjugates. I've written here get real because one use of these is that that multiplying a number, complex number, by its complex conjugate ends up having only real numbers. So this is that multiplication of a number by its complex conjugate is an important operation, which results in only a real part, which is the real part squared plus the imaginary part squared. Okay. If we add the number and its complex conjugate, we do also get something that's only real, but it has twice the real part. And if we subtract the complex conjugate from the number, we do get 2i times y. So one way to calculate the real part of the real component of 1z is adding it to its complex conjugate and dividing it by 2. The imaginary part is 1 over 2 divided by 2i to subtraction. And note this imz returns the imaginary part as a real number, not with the imaginary unit. And if this happens to be a real number, then the complex conjugate is just itself. So we have here noted that complex conjugate is the reflection. So if we're having a coordinate system here, okay, my draw pad here is slightly slanted. So if we had here a complex number, then a reflection over the real axis would be, so if this is z, then z is the reflection there. And a useful property is that if we have a conjugate of addition, it's the same as addition of conjugates. So this is transitive that way, and subtraction and also multiplication and division. So if we're needing to, so we can pick which one is easier to do. And just keep on taking conjugate of conjugate is itself, so we can take shortcuts as necessary. And we're going to show this. Okay, we calculated these operations for the numbers themselves for some time ago, and so we can just calculate the conjugates easily. So we had 17 plus I for the sum. So complex conjugate of that should be 17 minus I. And so complex conjugate of Z1 is 8 minus 3I. And then complex conjugate of Z2 is 9 plus 2I. Sum these up, we've got again 17 real numbers and minus I imaginary units. We've got 17 minus I. And the same for subtraction. You can, if you want, you can pause and go through these. So 1 here is a bit odd. It should be probably longer, but yeah, that's for the... This might be easier to comprehend if we draw it with parentheses on. So you don't mix it with complex conjugate of Z1 divided by Z2. Multiplication and division. Similarly, we should have 78 minus 11i for the complex conjugate product. So let's see, 8 minus 3i, 9 plus 2i. Real parts still stay the same because there's no change in the real parts. So let's recalculate the imaginary part, x1 times y2, 8 times 2 plus x2 minus y1, 9 minus 3, 9 times minus 3, we get 16 minus 27, which is minus 11, which it should be. And the same for division, we should get minus 43 over 85. Well, the divisor or the nominator here stays the same. We have squares there, so okay, we do have change in the sign, but it doesn't really change anything here because these are considered real numbers. And we still get the same numerator. Okay, so here's the idea. If we had complex numbers in a coordinate system, maybe we could represent them in polar form. So x equals r cos theta, y equals r sine theta, and the complex number itself, z, is r times cosine theta I sin theta. And yeah, there's a missing I over here. So no, there isn't. Yeah, so of course then the whole z equals x plus iy. So that's where the I come from. Yep, and r is the absolute value of the, so now we have a new concept. So r is the absolute value of z, which is the length of the vector really, so that's the r here. Same as with the regular polar coordinates, and it's calculated exactly the same. And now we note that there's a nice property here. We have the Pythagorean theorem, so that the length is square root of x squared plus y squared, and it happens to be the same as square root of the number multiplied by its complex conjugate. And the argument can be calculated by the angle, so y over x for non-zero x's, and I guess non-zero y's. Well, y is, well, we know it's 0 anyway. And typically we want to tend to be on within a certain rotation, so we include plus pi, and minus pi is not included, so this means that we limit that capital A argument of z must be greater than minus pi, and it can be up to pi. So if you're having a negative real number, so if we're having, say, minus 9, then in this form it does have an r of 9, and argument of minus 9 is pi. And triangle inequality states that if we add two vectors, then the result, or the length by going via two vectors is always greater or equal to the length of their resultant. So if those vectors would be the same direction, that is, if we're having the same argument for two complex numbers, then adding those two will result in something that has double the argument, double the value. But if we add two complex numbers that point in the different directions, then well, this wasn't not quite same direction, then the resultant vector is not as long as these lengths would be individually. So if this is Z1 length and this is Z2 length, then those together are greater than the resultant Z here. So this is why this is called the triangle inequality, because two sides of a triangle will be always longer together than the third side. If this happens to be a right angle, well, usually in this case it's not, then we would call this the hypotenuse. And this is what it means when this says verify by drawing. And this does generalize to any number of complex numbers. So if we just keep adding up these, then the resultant will be always shorter, or at most as long as the complete path by those components. Okay, multiplication and division follow form. Well, this is ridiculously easy. The formula to get those is here on the first line. Z1 times Z2, multiply the lengths, and whoa, you add the arguments. So if you have those in the form of the magnitude and the argument, or the modulus and the argument, then you can just add up those. So multiply the moduli and add up the argument, and you're going to get your new product. And now, going forward to the division, we see that for this to hold, then Z1 must be, so because these division and multiplication are inverse functions, inverse operations at least, then we must hold that the division times Z2 which should be Z1. So from that we can see that division, the modulus of division should be the modulus is divided. And arguments, the same thing. So in order to hold, then argument of this Z1 must be the same as argument of the division times argument of Z2, so argument of divisor. So after some manipulation here, then argument of divisor should be, so what we're saying here is this multiplication says that that if theta1 is the argument of Z1, then it must be the same as theta3, which is division argument, times theta2. And this is this here, well, arguments only, so actually we should put the args here, z1 arg z3 times arg z2, sorry, so not that one, but we remember this is argument of t. Yeah, getting tired. Let's try. So we know this part. So if argument of z1 times z2 must be argument of z1 plus argument of z2, then it follows that argument of the division, so times this, so argument of z1, yeah, exactly what it says here, so argument of z1 equals argument of that multiplication, which is argument of z1 by z2 plus argument of z2. So this will need to hold, and then if we want to calculate what this is just a subtraction, so let's do minus argument of z2 both sides. We get argument of z1 equals minus argument of z2 equals argument of z1 by z2. Okay, this is, as you notice, this is somewhat easy to confuse yourself, but we'll get this result here. And now we have this result, and we also have this kind of suggestion. Okay, product is product of the modulus of product is the product of moduluses. We also do get, by similar argumentation here, we get that the modulus of quotient is the quotient of moduluses, and we got those ones. So what is the polar form division? And since this is a recorded video, I don't need to pause too long. So if you want to think about it, how do you get a polar form multiplication division, then you should be able to do it by now, or pause the video and think. And let's go. So yeah, for multiplication we multiply the moduli and add to arguments. For division, divide the moduluses and subtract the argument of the divisor from the argument of the dividee. My previous example explanation was complicated. This is luckily rather simple. Not quite magic. We don't teach magic in the school, I think. Well, maybe in the arts department. But then one more thing. Okay, we do have a little connection to De Morgan's formula. So one might remember this, that cosine 2 theta is cosine squared theta minus sine squared theta. And we're going to show you how to get that formula. We might consider it as an exponential form. E to the power z is e e to the power of x plus iy. So okay, there's a plus sign there, which inherent in the z. Sorry. Where is my pause button? Alright, sorry about that. I might want to edit this video later on. But for now, busy for that, so let's go on. Alright, so exponential form, and by regular rules for calculating with exponential numbers, when we have a sum into exponent, then we can divide it as a product of exponentials. So e to the power of x times e to the power of iy, and the later part we can also present as cosine y plus I sin y. So the first part depends only on the real part, and the second part depends only on the imaginary part. So multipliers here can be just so if we take powers, then by the rules for the arithmetic for calculating powers, we can powers of powers become multipliers of powers. So we can put it right over there. So it's a similar form if we consider the exponential form that we can multiply to y there. We can see that the same form is that if we take cosine theta plus I sin theta to the power of n, we can just multiply that part there. So if we had cosine 2 theta plus I sin 2 theta, that's the same thing as if we put the 2 into the power. And if we calculate what that power would be by the rules of a plus b squared, then we can get that. So cosine squared theta, well, yes, and minus sine squared theta, the minus comes from I squared, that's minus 1, and sine squared, and then the middle part, that's the mixture, would be 2i cosine theta sine theta. And if we use only the real part of that, well, then cosine 2 theta is, so only the real part that is cosine 2 theta on the beginning, and cosine squared theta minus sine squared theta on the result of the expansion of the formula. And then one more piece of arithmetic, which is taking a root of a complex number. So we remember that a squared is b, then a must be plus minus square root of b. If we write this in polar form, then this whatever complex number z is r times cosine theta plus I sin theta, and we're having now square root here is really just the power of the reciprocal there. So the length ends up being square root of the modulus. So the modulus of the square root is the square root of the modulus. And then there we go. We apply the multiplier in front of the argument. So we get cosine theta over 2 plus I sin theta over 2. You could apply this even to real numbers, but then we'll need to consider that we're having well, that's theta is 0, so that goes to just 1 plus no imaginary units. But if we consider previous one, so that a equals plus minus b, then it's rather easy to see that we pop out another part there. This idea, so the minus part. So what it would look like is that we're having the, again, I'm having this slightly slanted, so let's try again by moving that, and remove handwritten data. So okay, now it's almost straight when I turn to, so we'll get to axis. So if we had, for example, square root of 2, we would see that the length would be somewhere around the square root. So square root of 2, and then if we want to find that what squared becomes 2, so x squared equals 2, it would be that. And if we also something that's on the opposite side of the circle. So with a square root we need to draw a line. If we had square root of something here, we would draw a line there. So the geometrical solution for any root would be that we draw a number on the complex plane. So for example, this complex number here, and well, this complex number here, and then we take radius of the, this is a typo, it should have an n here, so nth root of that, and draw the circle, and within the circle draw a polygon with the same amount of points. Well, in the case of square root, it's just a line through the origin to the other side, but then, for example, if we wanted cube roots, let's say 8, then, well, 8 is somewhere over here. Cube root of 8 on the real solution is number 2. And then we'd draw a triangle over here. And these points are also valid roots. If you take the cube, so power of 3 of these points, you will get 8. Let's see it in more detail. So cube root of 8, primary root is 2. We can verify this easily by taking 2 to the power of 3, that's 8. And then complex roots do have the argument. So this is, how did I get this 2 over 3? So consider that full circle equals 2 pi. Now each angle of the triangle is 1/3 of a full circle, so that is 2 pi over 3. So for nth root of x, well, nth root of z really, then we get arguments of of 2 pi over n times k, because they would be where k equals from 0, 1, n minus 1. So minus 2 over 3 pi, that is the same as 4/3 pi if we go from here. And yeah, this is the reason why if you calculate e to the I over pi, well, pi is there to argument, you will get it over there. Alright, and this is it for today's lecture.